Today we are having the topic AVL search tree. So before attending this session, you should already aware about the binary search tree. And if it is not the case, then please see previous one. So AVL search tree is the extension of binary search tree, because all the property of binary search tree is applicable here. And the issue we had in binary search tree of imbalancing, that after insertion operation or after deletion operation, in general there are the condition that if the operation of insertion tree becomes skewed, whether it is left or right, and the same case for deletion, then the actual benefit of binary search tree we will not getting. So we need to balance our tree. So the next and the first balance tree we have, that is AVL tree. So what is AVL tree and why we say it AVL? The discoverers, we have three name: Adelson, Wilski, and Landis. And the name of these three, we have this AVL tree, A, V, and L. The first character of three discoverers. Now, what is AVL tree? So, any AVL tree will be a most, it should be a binary tree. And this point is the important point for AVL tree. The difference between left subtree and right subtree height should be at most 1. So height of left and right subtree differ by at most 1. See this example. Here at this node 12, we have the height 1, 2, and 3. So the height of left subtree is 3, and the height of right subtree is 1 and 2. So the difference will be 3 minus 2, that is 1. 3 minus 2, that is 1. So at this node, we have the difference of minus, sorry, plus 1. 3 minus 2, 1. At this node, the height of left subtree is 1 and 2, and the height of right one is 1. So 2 minus 1, that is 1. Again, here at this node, 1 and 1, that is 1 minus 1, that is 0. So at this node, 1 minus 0, that is 1. So we can see at each node, the difference of the height of left subtree and right subtree, we have either 1, 0. So at most we have 1. So that's why we will say it is AVL tree. Now see this example. Here at node 12, 1, 2, 3, 4. The height of left subtree is 4 and the height of right subtree is 2. So the difference become plus 2. So this property that at most 1, difference would be at most 1, is not satisfied here. So that's why it is not a AVL tree. So it is not a AVL tree. Now, a formal definition of AVL tree: any empty binary tree is an AVL tree, and a non-empty binary tree, a non-empty binary tree is an AVL tree, is an AVL tree if and only if and only if we are assuming that suppose TL is the left subtree and TR is the right subtree of this tree T. Similarly, HTL is the height of left subtree and HTR is the height of right subtree. That is, HTL is the height of left subtree TL and the STR is the height of right subtree TR. So, a non-empty binary tree will be AVL tree if and only if we are taking this as as a notation, if and only if both this TL and TR are AVL tree. So that is, it becomes a recursive definition. Both TL and TR are AVL tree. And the most important point, this one, mod of HTL minus HTR less than or equal to 1. This term HTL minus STR is known as balance factor. Is known as balance factor. So in AVL tree, the most important thing is this balance factor. So it's a simple mathematics. If mod of HTL minus STR less than or equal to 1, then we know that the balance factor of AVL tree can be either 0, 1 or minus 1. So that's why in the previous example we had balance factor 0 and 1. That's why we said it is a balance, it is balanced, and that's why we said that it is a AVL tree. But in the next example we saw that the balance factor was plus 2, and it is not allowed as per the definition of AVL tree. So that's why that tree was not AVL tree. So this is the formal definition of AVL tree. Now, AVL search tree. What is AVL search tree? AVL search tree is basically BST, that is binary search tree, which is an AVL tree. That means AVL search tree will satisfy all the property of binary search tree with additional property of AVL tree, that is the balance factor at each node should be either 0, 1 or minus 1. तो हम बोल सकते हैं कि यदि बाइनरी सर्च ट्री का जो हर एक नोड का बैलेंस फैक्टर है यदि वो 0, 1 या -1 है तो वो बाइनरी सर्च ट्री हम क्या बोलेंगे कि वो एवीएल सर्च ट्री है। तो कोई भी बाइनरी सर्च ट्री, कोई जरूरी नहीं कि एवीएल सर्च ट्री हो, लेकिन हर एक एवीएल सर्च ट्री क्या होगा, बाइनरी सर्च ट्री होगा ही होगा। So I'm again repeating, an AVL search tree is binary search tree, which is an AVL tree. That means it will satisfy this balance factor condition, that at each node the balance factor will be either 0, 1 or minus 1. Now AVL search tree, as I said, are just like binary search tree. So we can represent this AVL search tree by linked list. But yes, we have to store this additional information, that is balance factor. So at each node, we have to register this data, that is balance factor of that node. Now we will apply again search operation and insertion and deletion. So no difference in search operation. So as we applied the search operation in binary search tree, we will apply search operation in AVL search tree as well. So I am not going to discuss this search operation. If you are not aware, then please see previous videos. Now see this example. Here the balance factor we are representing in parenthesis. So the balance factor of each leaf node will be always 0. So balance factor of this node A and balance factor of this node D is 0. Now balance factor of this node, you can see left subtree height 1, right subtree height 2. So 1 minus 2, balance factor will become minus 1. Similarly at here, the height of left subtree is 1 and right subtree is 0. So 1 minus 0, 1. So at each node, we can see the balance factor is either 0, 1 or minus 1. So it is a AVL tree. Now we can see whether this is a AVL search tree or not. The left, it should satisfy the property of binary search tree, then this AVL tree will become AVL search tree. So left child have less value. This A is less than C. And again, all the element in the right subtree of C is greater than C. At this node G, its left child D is less than this, and at right side, no node. So at each node we can see it is satisfied the property of binary search tree that left subtree will have less value than that node and right subtree will have greater value than that node. So this is the example of AVL search tree. So this is all about the search operation. Now next, insertion. In insertion, we apply the same process as we did in binary search tree. So again, I am not going to repeat the whole process of insertion. So if you are not aware, then please see previous video. So inserting an element into AVL search tree is similar to that of binary search tree. But yes, in AVL search tree, we know that at each node, balance factor should be 0, 1 or minus 1. So if we apply insertion operation and it will be similar to binary search tree, then our tree may be imbalanced, yeah, unbalanced. So to make it balanced again, we use a technique. We use a technique and this technique is known as rotation technique. This technique is known as rotation technique. I will discuss this rotation technique in our next video. So there are four type of rotation techniques: LL, RR, LR, and RL in respect of the insertion in AVL search tree. So we will discuss in the next video. Enough for today. Thank you.